goes. And all right, so what do we have so far? We have a bunch of history, a bunch of justification. We have C equals lambda mu. Sounds like a fraternity. If I was going to do a sorority or fraternity, I would make mine lambda mu, just because. All right, and now we have something where we can find the energy if we're given the frequency. Okay, and we have Planck's constant, which is our new thing, which is 6.626 times 10 to the minus 34 joule seconds. All right, now, once again, it's all about units. Everything is about units. Okay, and so in this chapter in particular, so now, if I wanted to calculate, let's say, how many joules is one photon at, let's go out more towards the blue, let's say 305 nanometers. How many joules is one photon at 305 nanometers? Now, why in the world do I pick on nanometers? Because that's what light's usually measured in. Visible light's usually in nanometers. You're not going to be given the wavelength in meters unless you're talking about radio waves. If you're talking microwaves, they'll be in centimeters and millimeters. If you're talking radio waves, they'll be in meters. If you're talking visible light, it'll be in nanometers. If you're talking, even ultraviolet light will be out in nanometers, vacuum ultraviolet being, like 60 nanometers or something like that, and so forth. All right. So you're not ever going to see them in meters. So get used to the fact that you're going to have to convert it into meters. Now, it says here how many joules at this meters. Now look, units are important. What do we see over here? That's frequency. That's in seconds to the minus 1. Do we have seconds to the minus 1 over here in nanometers? No, we don't. We have the wavelength. Okay, we have the wavelength. Now, there is an equation where we can go directly from wavelength to energy, and I'm not going to use that because, you know what, if you have these two equations, you ought to be able to figure this out. And so what should we do? Well, what we should do is we should go from nanometers, we should write that out as meters. That's kind of like step 1. And then step 2, we should what? Solve for the frequency. Right? And then maybe step 3, then we should solve for E, which is in joules. All right, that's the way you should do it. Okay, we could take, one equation, and you can get it because it's like E equals, I think that's what it's C over wavelength something or another. All right, and so we can look it up. No big deal. It's actually on your formula sheet. But we don't need these things. We don't really need these things. What should we do? Well, you know what? Let's take this and put this in nanometers first, shouldn't we? So we say, you know what? 305 nanometers. I know what a nanometer is. That's 305 times 10 to the minus 9th meters, right? I know this. And so I say, you know what? I can find the frequency from this. And this is 3.00 times 10 to the what? 8th, I believe. And that's meters per second. And then we're going to divide by that 305 times 10 to the minus 9th. And we'll get something like 10 to the minus 10 to the 15th or something like that. And I put that in my calculator and I go 3 second exponent. I am sharing. Good. No one said anything. Let's see. 10 to the 8th. Divided by 305, second exponent minus 9, and I get 9.84 times 10 to the 14th. And that's per second. Okay, so I found the frequency. Now I can find the energy. And so I say, you know what? What's the energy? The energy is Planck's constant, 6.626 times 10 to the minus 34 joule seconds times 9.84, and I'm going to leave it in my calculator, times 10 to the 14th, and that's seconds to the minus 1, and look, seconds cancel, see? Seconds cancel. And now I'm left with the energy, which is a very small quantity. Now I'm leaving the frequency in my calculator. I'm not putting 9.84. I'm actually got 9.836065557. All right, I just leave it in my calculator for rounding purposes. And times 6.626 second exponent minus 34, and I get 6.52 times 10 to the minus 19 joules. That's a very small quantity of energy, but keep in mind, there's supposed to be an arrow, by the way. Keep in mind, this is for one photon. That's for one photon. Now, what you have zipping around in your room right now, or from a laser or whatever, is bazillions and bazillions of photons. And even though a photon in and of itself is a very small quantity of energy, if you got a lot of them, you will eventually add up to some energy, right? So if you had a bunch of them, then sure enough. And so let's say we have that, and I want to know how many joules is 1 mole of these photons. How many joules is 1 mole? And I just told you that one photon that we just calculated, one photon is what? 6.52 times 10 to the minus 19 joules, right? Okay, how many is in a mole of photons? Now that's a lot of photons. And so what do? We draw, hey, this is how we do dimensional analysis, isn't it? We draw a line, we draw another line, and we say 6.52 times 10 to the minus 19 joules, okay? And this is per photon. This is joules per photon, okay? And if I say, it's 6.022 times 10 to the 23rd per, that's particles per mole, okay? And that's per particle, and we multiply the two together, and we'll get photons are actually going to cancel because they're in the denominator. And so I'm just leaving that number in there, and go 6.022 times 10 to the 23rd of these things, 6.022 second exponent 23, and I get a whole bunch of joules, and I actually get 392,000 joules, which is a lot of joules, by the way. 392,000 joules. Okay, it's a lot of joules. That's for a mole of photons. Okay, and it takes about 4 joules to heat 1 gram of water by 1 degree Celsius. So that's a lot of water that you can heat up with that many joules. So, but my point of this, though, is that one photon is not very many joules at all, just one. But you get enough of them together, it amounts to something. Now, all right, so what do we have so far? We have lambda mu, Planck's constant mu. Now we have something called the photoelectron effect. Alrighty. And basically it works like this. If you have a clean piece of metal in a vacuum, we have shiny clean metal, shiny metal in a vacuum, and we shine light on it. Light hits. You will have, at a certain frequency, you will have electrons ejected. Electrons come flying off in all directions. Okay, electrons come flying off. All right, now below a certain frequency, let's say red light. Remember what I said? Red light's less energetic, blue light's more energetic. And below a certain frequency, nothing happens. Nothing happens. Okay? Matter of fact, no matter how intense, now this is counterintuitive. Remember, we're talking prior 1910-ish, after 1910-ish. If you were a scientist from the 1800s, you would say, well, you know what, I can make anything happen if I hit it hard enough. And if you hit this hard with even more light, in other words, I crank it up to 11 and I really get the light really hitting it hard, guess what happens? Nothing happens still. Nothing still happens. So the fact that you get electrons coming off doesn't depend on the intensity of the light. And that's counterintuitive, because you would think that if all I have to do is crank that dial up, and if I can get it cranked up high enough, if I hit something hard enough, stuff should be knocked off. Stuff should be knocked off. Now, if you plot this, and being sciencey sort of people, we love graphs. If you plot this, you will see that the intensity, or the number of photons, let's change that to just number of electrons. The electrons, number of electrons coming off, and here's 0, and here's the frequency, or the energy, as we're going this way. You will see that as you increase the frequency, there are no photons, and then at some magical point, depending on the metal, you start getting electrons. And the energy of those electrons as they come off, actually it's not the number of electrons, let me change this. The energy of the electron increases as you come off. So at some point, you have no electrons come off, and this is called the photoelectron effect. Okay, so you have to have a minimum amount of energy from the photon to kick that electron off. In a roundabout way, this is the binding energy of the electron on that clean metal surface. Okay, and does anybody know what Albert Einstein? Ever heard of Albert Einstein? Everybody's heard of Uncle Albert. All right, and you know what he won his Nobel Prize for? And if you ask the average person, what did Albert Einstein win his Nobel Prize for? They would say, oh, that's relativity, right? That's relativity. And if you're on Jeopardy, Alex Trebek would say, no, that's wrong. No, Albert Einstein won his Nobel Prize for the photoelectric effect. That's what he won his Nobel Prize for. He went on and did all this other stuff, but that's what he won his Nobel Prize for, was the photoelectron effect. And you can actually calculate, what is going to be that minimum amount of energy that you can inject an electron. And so if you're told that the binding energy is so many joules per electron or whatever, you can use these equations over here. And I'm not going to go through it, but basically you just use these equations. You plug in that frequency and you can get the energy. There it is. That's as simple as that. That's photoelectron effect. So basically, this is another evidence of quantized energy. that there is a quantum effect, that there are levels that you have to have a minimal amount of energy for a photon for that electron to be ejected. And it doesn't matter how many you hit it with photons. It doesn't matter how many you hit. Now, for those who are planning on going on to grad school one day, this is not quite completely true. You can actually take photons, do a diagram that our physicist friends like to do, and you can actually combine photons together, and you can actually get a photon that comes out that's like ×2 the energy. And if you hit it hard enough, you can actually turn some of these red ones into blue ones. Yes, you can. With the appropriate nonlinear optics, you can actually make this happen. So, but anyway, that's the photoelectron effect. Now, a little bit more history here, because all this stuff figures back on history. Now, remember our red light, not a red light, but our black body radiation. And we said, or I said, that depending on the temperature, you could get a different distribution just depending on the temperature, right? And we said, you know what, it's a really smooth curve, it's very easy to predict. And Planck comes along and he kind of puts a tweak in there and says, you know what, it's bounded, we have to bound it somewhere. Okay, now this sort of stuff has been known quite some time, and then someone back in the day, we started getting these things called discharge tubes. Basically, they're glass tubes where you pump out the air until you have a vacuum. You put some high voltage across it, bzz, you know, a little zap 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 going on in between. And if you put a little bit of, say, neon in there, just a little bit, and we're talking just a little pixie dust amount of neon, this glass tube will put out red light. You get a red light. Matter of fact, this is a neon light. And just so if you're ever on Jeopardy, what is the light of a neon light? And people say, well, neon lights, I've seen those. You've got green ones, you got blue ones, you got yellow ones, red ones. Neon lights are red. If it's red, it's neon. If it's oxygen, it's green. If it's nitrogen, it's blue. So whatever you put in there determines the color. All right, and sodium, by the way, is yellow. So depending on what atom you put in these tubes, and by the way, the fluorescent lights, if you go into an office or at school or something, you see those fluorescent lights that are in the ceiling, those have mercury in them. And mercury puts out ultraviolet light, but it hits a phosphor. In other words, phosphorus containing materials that are on the inside, that white powder, if you ever bust one open, and it converts it into visible light. Okay, and you may say to yourself, all right, fine, Mr. Pierce, you just showed us, you know, where the neon lights come from. Well, that's how a neon light works. Okay, but if you take this light from this neon light and you put it through a prism, y'all have seen this. You ever seen Pink Floyd? You know, the album Dark Side of the Moon. You know, it's got a prism on it, and it has a spectrum, right? And it actually shows a rainbow spectrum, and that's a continuous spectrum. That's one of these guys right here. And if you take some light from the sun and split it apart, you'll see a rainbow, right? But if you take that red light and you split it out, you will see what looks like this. You'll see a very bright red line. You'll see a lot of empty space. You'll see maybe a very faint pair of green lines. And maybe as you go further out, you'll see maybe a very, very faint set of blue lines. And nothing in between. And this was seen back in 1800s, and this is called a line This is a line spectra. Spectra. Line spectra. Because it has lines for the different wavelengths of light. You don't see this. This is continuous. That's a continuous spectrum up there. It's got all the frequency in it, and it's got all the wavelengths in there. This is only like that. And this, back in the late 1800s, when vacuum technology got good enough to make these glass tubes with vacuums, and we're able to put materials in them and put electricity across them in the late 1800s, this was a great mystery. Because you see, I can predict that continuous spectrum. That's a Boltzmann distribution, very well understood. Even if you have to bound it with Planck's constant or whatever to get it to work, it's still very easy to predict. You can't predict these lines based on that kind of equations. You can't do it. And so this puzzled people for quite some time. And so finally you had this guy called Bohr, Niels Bohr. Bohr comes along and he says, you know what, I got this figured out. Let's take a look at Planck's constant and this whole idea of minimal amount of energies. And what he says was, you know what, atoms are like this. They have different orbits that the electrons can whiz around in. They're whizzing around on the outside of these atoms. And when they change energy levels, when they go from one to the next, or when they fall down from one to the next, you have energy comes out. Or like if you go from, say, here to there, then you'd have, a different frequency of light comes out. And let's say you go from here to there, you would have, let's say, green light come out. So as the electrons change energy levels, you end up with different frequencies of light, different wavelengths, and therefore different colors. But you can only go in between these discrete levels. In other words, there's no halfway. And so if you do that, and another way of looking at this instead of the Bohr diagram is you look at it in terms of energy levels, and you do like this. Here we go. Let's see. I'm going to try to sketch this out so y'all can see this. Alright. Okay, and we have these energy levels 1, 2, 3, and 4. And if you put an electron in these energy levels, and energy is going up, by the way, like that, and you jump, say, from here to there and back, then the energy that comes out is the difference between the energy between these two levels. You got E1, you have E2, and it's the difference between these two. And you have, let's say, red light come out. And let's say you jump from, say, here to there and back to there, and you have green light come out. And let's say you jump from here to there and back, and you have blue light come out. Now remember what I said, as you go further to the red, your lower energy. As you go further to the blue, your higher energy. And so the distance between jumping from one to the next tells you what the energy level is. And Bohr says, well, that's how this is working right here. You have most of your energy is going from, this guy right here is going from n equals 2 to n equals 1. And then you go down over here to where you got a couple of green lines, very faint green lines. That's why you see red, is because that's all your eyes can see. And you say, you know what, this is going from 3 to 1. And you go further out into the blue and you see this where you have 3 lines, and you say, you know what, that's going from 4 to 1. And the reason why you don't see anything out here is because you don't have anything in between. You just don't have these things. If they're not there, you can't see it. Remember what I said at the very beginning. If it's not there, you can't see it. There's no energy levels in between. If they aren't there, you can't see it. And so sure enough, we don't see anything where these blue X's are because there's nothing there. There's literally nothing there. Now these energy levels, now I'm going to caution this, because you see when you look at Bohr diagrams, which by the way are not really all that real, it almost implies that your electron is jumping in a physical position. Kind of like this is a building up here and I physically go from the first floor to the second floor. Keep in mind, this is not position, this is energy. Just like as if you're driving a car. Let's say you're driving a car. I'm going to draw a picture. Here's my car. Driving along, right? Your position from X to Y. Now that is a position going from here to there, from X to Y. From Greenville to Raleigh, that's a position. But how fast you're going doesn't depend on your position, does it? Depends on how fast you're going, the energy. So this is literally, this is energy. This is not a position. You're not changing position. You're just changing the energy. Okay, you're changing the energy of that electron. Okay, now we have this line spectra here, and Bohr kind of explains it, and another guy comes along, he's called Rydberg, and Rydberg, now Bohr said this is because we're flippy-flopping between energy levels. He still couldn't tell you, how do you get these lines and how can you calculate them? And Rydberg comes along and he says, you know what, I have an equation for you, and it goes like this: the energy is some constant known as a Rigberg constant, R sub h, and it is 1 over n squared final minus 1 over n squared initial. This energy, if you take these n levels, see how I've got these labeled as n? You see that? If you know you're starting in, and if you know you're ending in, you can calculate the energy of that transition, and it's called a transition. When you go from energy level to energy level, it's called a transition. So when you transition from 1 to 2 and 2 to 1, and you plug in the numbers, you'll get that guy right there, the red line. And when you plug in going from 3 to 1, well, you'll get this number right there. And you plug in 4 and 1, and guess what? You get that one right here. You get the same sort of thing. You get the numbers. And in fact, R sub h, you see that h there? That constant, it's an experimentally determined constant. That constant actually depends on what it is. Now for the hydrogen atom, R sub h, and I won't put it down, you can look it up, it's in the back of the textbook, it's called the Rydberg Constant, it's a number, alright? That number is one of the best known numbers in science, R sub h. It is known out to a precision. Remember what precision is? Precision is how many decimals you go out. It's not accuracy and precision are not the same thing. It is one of the most precisely determined constants of everything. R sub h, I don't know how many decimal places it goes, but it's a long ways. It's a bunch of decimal places. All right, for R sub h. So for a hydrogen atom, you can calculate the position of these lines to an incredibly precise number. Incredibly precise. You just plug in the numbers, and you'll get a energy which corresponds to a frequency or a wavelength that you can measure. And you go out and you measure and you say, my gosh, we are onto something here. I can predict this right here. I can predict this spectrum. Yay, I am so happy because you know what? As a scientist, if you can make predictions and the more decimal places you can go out, the happier you are. The only problem is that when you go out and you try to predict anything other than hydrogen, it doesn't work very well. For hydrogen, for H atom, E equals R sub H, that's in your textbook, 1 over n squared minus 1 over n squared final minus initial works very well. Very well. And for everything else, it's terrible. Now, when I went through your position here, and I was doing this years ago, we spent some time, calculating the emission lines and absorption lines for hydrogen atoms, and you can do this. You can put this in an Excel spreadsheet and generate all the transitions you want. Matter of fact, if you do this lab where you calculate, let's say you go on to say NC State or something, and one of the labs is, if you take a spectroscopy lab, they might ask you to calculate and predict hydrogen atom transitions. Here's a pro tip: use a spreadsheet. Don't try to calculate it by hand, just use a spreadsheet. All right, you plug in your N1, N2, you got a formula. If you know how to use Excel, you know what I'm talking about. All right. The problem is that this doesn't work very well for anything other than hydrogen. You try to do this for helium, and there's an R sub He. You do this for helium, and you sort of get a good fit, sort of. Now compare that to, oh my gosh, this is such a beautiful fit, and no matter what you do, this is perfect, beyond perfect for hydrogen atom. But for helium atom, it's like, well, it sort of fits and it sort of doesn't. And by the time you get to lithium, it doesn't work at all. Now you got to keep in mind this Rydberg equation up here was actually, Rydberg was a mathematician. He wasn't a physicist or a chemist, he was a mathematician. And this is actually a series. If you take Calc 1 and Calc 2, you deal a lot with series. This is one of the series. This is a series. It's a difference of reciprocals. All right, it is a series, and he recognized, he saw the lines, and this is how mathematicians think. He saw the lines in the spectrum, and he says, "Aha! I know the equation." And he said, "Here it is. Here's your equation." Unfortunately, it doesn't explain what's going on. It just fits very well, and for everything else, it's terrible. Now, why does it fit so well? And the answer is because of this. Why does it work so well for hydrogen and not for everything else? Well, look at hydrogen. What is hydrogen? Hydrogen is a proton with an electron whizzing around it, right? You can calculate the attraction here. The energy is very well known. It is the Coulombic constant times the charge of the proton times the charge of the electron over the distance between the two. Okay, and this is very easy to calculate. And you can actually, and you set this up so that you have an angle, and you use polar coordinates. You have an angle and a distance, and if you put this in here, and 5 pages of algebra later, you come up with this. Okay, this is called from fundamental constants. You can do this, believe it or not. If you sit down with your buddies and brainstorm this, you could probably duplicate the wave function for a hydrogen atom. I had to do it in grad school. It's not that bad, 5 pages of algebra. And so you can get that. The problem is that when you get the multi-electron systems, you have 2 protons and you have 2 electrons, right? That's helium. Now you have this interaction, D1. Now you have this interaction, D2, or R2, or R2, whatever, it doesn't matter, okay? But you also have another interaction, don't you? You have a repulsion between those electrons. Now you have a multi-body problem, which is not solvable for right now. Exactly. It's not solvable exactly. So when you start getting the multi-electron systems, you need a really big computer. You have to pull out some different kinds of math, and you get approximate solutions, which get pretty close, but this doesn't work anymore. Okay, so this is a lucky accident, which is why I don't really care a whole lot about, other than to say that it was the first equation that came out that actually described these line spectras. It was the first one that came out, and it fits very well, but it's only because of this guy over here. You have a two-body system. It is solvable exactly. And so sure enough, you get an exact equation. But if you go beyond more than one electron, which means helium and everybody else, and molecules, which are obviously more than one atom and more than one electron, it breaks down in a hurry. It breaks down in a hurry. So you still need to spend some time on, do a couple of these calculations with the Rydbergs in the textbook. There are some example problems, just so you can convince yourself that it does work and that you can get, very precise answers for hydrogen atoms. But understand, and this was not explained or said to me or articulated, it doesn't work for anything else. So it has very limited usefulness, the Rydberg equation. And the only reason why it's presented is because it works really well for one atom. But for anything else, it doesn't work. Okay? Alright, so keep in mind there is that equation in your textbook. You should do some examples because you never know when it might show up on a homework or a quiz or something like that, right? It's like a lot of things in this world. You have to duplicate what the previous person did before you can move on to the bigger and better stuff. All right, so you should be able to do that. So what do we have so far? I like doing that. Let's summarize what we have so far. Kind of chapter 3, I did the same thing, right? What do we have? How do we put it together? So what do we have? We have C equals lambda mu, and we have energy of one photon is Planck's constant times that frequency. And what do we know here? Always meters and seconds, right? Always. If you put in something other than meters and seconds, you will get an answer and it will be wrong. And our next equation that we have is R sub h squared. And this is the Rydberg. And it's really only useful for hydrogen, but you still need to be able to do it, all right? And it's just a plug and chug. These are all, I'm not spending a whole lot of time setting things up because there's nothing really to set up. It is a plug and chug situation. It's not like you have to go through the problem, figure out what you got grams of, balance an equation, all this other good stuff. You need to know the wavelength, you need to know the frequency, you need the energy, or one or both or all three, whatever. You need these things. But at the end of the day, you're just going to plug in the numbers and get an answer. But you have to be very careful. Very careful about things like that, okay? Very careful. And of course, energy is always in joules. So if you have millijoules, what do you think you have to do? It's times 10 to the minus third joules, right? Yeah. So these prefixes really do matter. Okay, they really do matter, but beyond that, it doesn't really matter. And take some time and go over the photoelectron effect in your textbook. Just take some time to go through it. It's very interesting, the whole, implications of what's going on with the photoelectron effect, okay? So, what are we doing next time? Well, we're going to continue with something called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle basically says you can't know the position if you know the velocity or momentum, and you can't know the momentum if you know the velocity very well, or the position very well. Okay, we'll get into that. It's kind of like another one of these plug and chug kind of equations. You just have to be careful about your units. Anytime you're going to do one of these, what do? What do I do when I'm doing these equations? What does Mr. Pierce do? I just look up the equation, I pull out my calculator, and I plug and chug. That's what I do. Okay, when I'm using these, that's all you can do with these is plug and chug. That's my point. But like a lot of things that look really simple, yes, you are plugging and chugging, but what happens if you don't use the right units? That's what I'm saying. Okay, you got to make sure you're using the right units. That's the big deal. That's the big deal. But you'll be surprised how many of your colleagues, when it comes time to do this, will use the wrong units. And me and my other friends, from down the hallway, we stand around and we got little tears coming down our face because we're like, what else can we tell you? Use meters. All right, so that's what we got there. So, and we'll continue on with that, and we will finish Friday with this. We have to do stuff about orbitals, and orbitals is where you expect to find electrons. We'll have to do allowed versus not allowed electronic configurations and things like that. Okay, so there's still a lot of more stuff to cover, but we'll finish it on Friday. We'll finish. Okay, so let me go ahead and stop recording real quick here. So let's see, stop.